Let's review the principle of mathematical induction. So the principle says the following. Suppose that for each positive integer n, there corresponds a statement e of n, which is either true or false. Suppose further that e of 1 is true, and whenever e of n is true, then so is e of n plus 1 for all n. Then we can conclude that e of n is true for all n. So in order to prove that e of n is true for all n, we have to establish 1 and 2. So just to give you guys a silly example, let's say we want to prove that the sun rises in the east every day. So let's say today is day 1 and tomorrow is day 2 and the next day would be day 3 and so on. And we want to show that the sun will rise in the east each day. And so let's say that somehow we prove that whenever the sun rises in the east someday, it rises in the east the following day also. So again, let's say we have a way of showing that whenever the sun rises in the east one day, it rises in the east again the next day. And now let's say on day 1 we check that the sun rises in the east. Well, so now we can use what we have shown. So on day 1 we can check that the sun rises in the east. Well, since it rises in the east on day 1, it must rise in the east on day 2. If it rises since it rises in the east on day 2, it must rise in the east on day 3, and so on. So you can see the argument, how it works. There is a little bit of a different version of this principle. So here is an equivalent form of the principle of mathematical induction, which says the following. Again, suppose that for each positive integer n, there corresponds a statement e of n, which is either true or false. Suppose again that number 1, e of 1 is true, and number 2 is that if e of m is true for all m strictly less than n, then e of n is true. Then we can conclude that e of n is true for all n. So you can see that that only number 2 is different. So in number 2 now, here we are saying whenever e of n is true, then e of n plus 1 is true. Here we are saying whenever e of m is true for all m less than n, then e of n must be true. So in terms of my silly examples of the sun rising in the east, so the condition number 2 says whenever the sun rises in the east on day n, it must rise in the east on n plus first day. Here in this number 2, in terms of my example, it says if the sun rises in the east for all days from day 1 up to day n minus 1, then the sun must rise in the east on the nth day. Again, this number 2 says if the sun rises in the east all days before the nth, all days up to the n minus first day, then the sun must rise in the east on the nth day as well. Okay, so let's explain this further by using an example. Let's say we want to prove that for all integers n greater than or equal to 1, the sum 1 plus 2 plus dot 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 plus n is equal to n times n plus 1 over 2. To prove this by induction, here's what we do. The induction proofs always have two steps: the initial step and the inductive step. So that is the number one here is proving number one here is the initial step, and proving number two is the inductive step. So the initial step is, okay, when n is 1, is this equation true? Well, let's see, when n is 1, the left hand side has only one term, which is just 1. So the left hand side is equal to 1. And on the right hand side, I get 1 times 1 plus 1 over 2, which is 1. So we see that when n is 1, the equation is true. So the desired equation holds true when n is 1. So that's my initial step. That is, I want to prove that the statement is true for the initial value of n. Now the inductive step. Now we want to show that whenever the equation is true for n is equal to k, it must be true for n is equal to k plus 1. So if the kth statement is true, then the k plus first statement must be true. So we say, okay, let's assume that this equation holds when n is k. So that is, we are assuming that 1 plus 2 plus dot 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 plus k is equal to k times k plus 1 over 2. Now we want to prove that the equation must also hold when n is k plus 1. So when n is k plus 1, what's the left hand side? The left hand side is 1 plus 2 plus dot 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 plus k plus 1, which is equal to k times k plus 1 over 2. Okay, so if you look at the sum of the first k terms, by our inductive hypothesis, this is k times k plus 1 over 2. So that's what I'm plugging in for the sum of the first k terms, and then I have k plus 1. So now we do algebra. So this would be k squared plus k, and then 2 times k plus 1. So that would be 2k plus 2. So I get 2k plus 2 here, and k squared plus k. So that's k squared plus 3k plus 2 divided by 2. Now, the numerator can be factored as k plus 1 times k plus 2. So we get k plus 1, k plus 2 over 2 by factoring. And so that's exactly should be the desired right-hand side when n is k plus 1. So notice that when n is k plus 1, we should be getting k plus 1 times k plus 2 over 2. So that's exactly what we got. So we see that when n is k plus 1, the equation is true. So assuming that the equation is true for n equals to k, we were able to prove that the equation is also true for n is equal to k plus 1. Therefore, by the principle of mathematical induction, the equation is true for all n. And here's here are 3 exercises on using the mathematical induction, and I'm gonna be stopping this video on this slide 6, and in the next video we will start talking about relations.